We are in Semester 2 Physics. We are currently in Unit 2, Magnetism and Electricity. Our topic for today is going to be electric charge. Electric charge. For odd periods, this will be due on Wednesday, February 26th. For even periods, this will be due on Thursday, February 27th. Before we start talking about electric charge, we first need to talk about what everything in the world is made up of. And anything that is a physical substance is what we call matter. So everything that you see around you, even, for example, the air is still a physical substance. It's made up of matter. It's just really, really small. You can't really see it. So everything that, so matter, for example, let's think of a drop of water. Now, if I were to break down this drop of water as small as possible, and I take apart even smaller drops of water, until I get to the smallest amount of water that I can have, I would end up with the atom. And the atom is the smallest unit of matter. So if I go any smaller than the atom, then I no longer have any water. Okay, so atom, smallest unit of water. From there, so in terms of size, we're going from matter down to the atom. And from there, we're going to go down to what are called subatomic particles. And subatomic particles, essentially, are going to be the different parts of an atom. And that's really where we're going to focus today in order to learn about electric charge. So when you guys get to chemistry next year, you'll learn a little bit more about what elements are. And essentially, elements are just kind of the different parts of matter that make up life. And today what we're going to focus on, because it's the easiest and the smallest type of element, is going to be hydrogen. We can find hydrogen in things such as water, or hydrogen peroxide, which is what you put onto cuts. It can be found in, for example, ammonia. It can also be found in methane, which is a type of gas that we use. So basically hydrogen, it's just what we're going to be looking at today. So this right here is actually what a hydrogen atom looks like. This is how we draw the diagram. And for the most part, remember that the hydrogen atom is extremely small. Like, this is a super blown up picture of the hydrogen atom, because in reality you wouldn't be able to see it. But if we look at it in the center of the hydrogen atom, in what's called the nucleus, which means the center of the atom, we have, in this case, one proton. And around the hydrogen atom, kind of in a ring around our nucleus, we have the electron. And the important thing for you to know is that protons, sorry, we have one electron, protons are positively charged, and electrons are negatively charged. And so as we're going to be looking, and so these two things, the electron and the proton, are what are called the subatomic particles that I talked about in the previous slide. Subatomic particles. So these subatomic particles are what we're going to be focusing on, because in physics we talk about positive charges and we talk about negative charges, and you'll see as the unit goes on what I mean by this. But what you need to know is that this is how we get this positive charge, a proton, and this is how we get a negative charge, an electron. We have a way to actually measure what charge is, and the charge of a proton we label as positive Q, and that equals 1.6 times 10 to the negative 19th as our exponent, and the unit is a big C for coulombs, which I can go ahead and write here, C-O-U-L-O-M-B-S, coulombs. So that's the charge of a proton. However, in most things around our world, we don't get shocked by anything whenever we touch it, for the most part, which actually means that there is no charge overall on things. So if our proton has a positive charge of 1.6 times 10 to the negative 19th coulombs, then this electron must be balancing it off right here. So our electron is what we call negative Q, and that is going to be negative 1.6 times 10 to the negative 19th coulombs, which is how we end up with a no charge overall, because our positive Q plus our negative Q ends up being 0. So remember how small this charge of 1.6 times 10 to the negative 19 coulombs is? We need to kind of remember this idea of scientific notation. Remember, I have another video on scientific notation. You're welcome to look back at that. But just a really quick rundown. Remember, we go ahead and we write this number right here, 1.6. So I'm going to write it over here because I need the space, 1.6. And then this negative 19 tells me that I need to move my decimal place 19 times. And because it's negative, I need to move it so that I'll end up with a smaller number. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And in these places, I would add a whole bunch of zeros. And remember that my decimal place goes all the way at this beginning point. Sorry, it's a little bit tough to see all the way at this beginning point. So the decimal point moves. So I end up with this number that looks like 0.00000016. So we end up, and we can no longer see the decimal point over here. It should just end up being this number. So it's a really, really, really small number, a really, really small charge. So this many coulombs. So keep in mind that because protons and electrons are so tiny, their charges are also tiny. But because we have a whole bunch of them at any given point, that's why we are able to, for example, feel shocks from like when we touch a piece of metal, for example. At this point, we're going to kind of compare what we've already learned, which is magnets, with electric point charges. So those subatomic particles, from now on, I'm just going to call them point charges. So for a magnet, remember the magnetic field, so remember B for magnetic field, can be drawn using lines. So remember the lines go from north to south, like so. So the arrow should be pointing towards the south. It should always be symmetrical. We always have arrows pointing into south and arrows coming out of north. So that's what a magnetic field, or B, looks like. For an electric point charge, those also have fields. However, these are going to be called electric fields. And the way that we abbreviate electric fields is we call them a capital E with an arrow. So it is a vector. And it's kind of similar to this idea of our magnets, where the magnetic field comes out of the North Pole and into the South Pole. For electric charges, the electric field will come out of the positive charge. And then for negative charges, the electric field goes inwards. So right now we're just talking about them independently. We're pretending that they're currently separated from each other. So they're not next to each other. And if this were the case, electric field would point outwards from our positive charge and inwards for our negative charge. Remember that when we have two magnets next to each other, if their opposite poles are next to each other, they will be attracted to each other. The same is true for electric point charges. If we have two opposite charges, they will be attracted. So I'll go ahead and write attracted right here. And for magnets, we can go ahead and draw the magnetic field B. And remember that the arrows, again, go from north to south. And because they are attracted, we're going to see a bunch of field lines going between the two magnets, like this. It looks very similar for electric point charges if we have two different ones. And we're going to end up having them go from the positive charge to the negative charge. So our electric field is where the electricity can affect other things, and it's going to look something like this. In the same train of thought, for magnets, if we have like poles next to each other, so you can see North Pole next to the North Pole, these ones are going to repel. And again, if we have two of the same charges, so like charges, those will also repel. For magnets, the magnetic field B, we can draw, again, it moves away from the North Pole towards the south, away from the North Pole towards the south, north to south, north to south, north to south, north to south, and they're repelling each other. So at this point right here, I have absolutely no magnetic field because those don't want to be next to each other. Very similar for our electric point charges. Remember, the electric field E moves away from positive charges. So what it's going to end up actually looking like, because they're repelling each other, is that their fields are kind of going to bend away from each other. So it ends up looking something like this. Alright, so this one is showing repelling. At this point right here, we have no electric field. You'll see in this picture that we still have like poles and like charges. However, in this case, we're looking at negative charges. So for magnets, the magnetic field B, it would look very similar to the previous one, but in this case, the arrows go from north to south, north to south, north to south, and north to south. However, in this case, still, they are repelling from each other, so at this point right here, we have no magnetic fields. These magnets will not be attracted. They will repel each other. Similarly, for negative charges, remember that for negative charges, the electric field E goes into the negative charge. So we can go ahead and draw this. It's going into the negative charge. But again, these electric fields are going to move away from each other. So they're going to have an empty space right here where there is no electric field. Alright guys, that was a lot of information. Make sure that you take really good notes and that you are ready for your homework quiz. See you later.